Welcome, folks. I want to give several further examples of group homomorphisms. So let n be an integer. We can define a map from the integers under addition to the integers mod n. Just by sending an element j to j mod n. Okay, and if I had to draw a picture of this, maybe I have the integers, and then let's map to the integers, say mod 3. Okay, so in the integers I have -4, -3, -2, -1, 0, 1, 2, 3, 4, etc. And they're all getting mapped to either 0, 1, or 2. And things are periodic. So -4 is the same as -1, which is the same as 2 mod 3. -3 is the same as 0 mod 3. -2, I add 3 to get 1. Okay. -1 is the same as 2 mod 3. 0 takes me back to 0. 1 is the same as 1. Okay. So probably I should color these, but every third element maps to the same spot. Okay. And then here, these elements all map to the same spot. And these elements, etc., all map to the same spot. Okay. Let's look at an example from permutation groups.
Hey, Henry.
Yeah.
On that last one, you wrote that n is greater than or equal to 0. Was that not intentional?
You mean here?
Yeah.
Oh, I mean, I didn't want to consider z mod 0z.
Oh, sorry. I was mixing up j and n. Sorry about that.
Oh, no worries. Yeah. What is z mod 1z? I guess z mod 1z is just here. Yeah. Z mod 1z has all elements from 0 up to 0, right? This is just the trivial group. Right? So it turns out that any group has a homomorphism mapping to the trivial group that only has one element, the identity. You just map every element to the identity. Yeah. All right, I want to describe a homomorphism that begins with the symmetric group. So it begins with permutations, and it maps down to z mod 2z. Okay. So let me tell you how I define this. Sigma is going to be my permutation, or maybe I'll call it alpha. We're going to map alpha to either 0 or 1. And it's going to map to 0 if alpha is even. In other words, alpha is an element of the alternating group. And it's going to map to 1 if alpha is odd. In other words, if alpha is not in the alternating group. This is a homomorphism. And let me show you a picture of it. So here's a picture of, on the top we have S3. Okay, so these are all the permutations of 3 elements. We have the identity permutation, a 3 cycle, another 3 cycle, and then our 3 transpositions. Okay, some of these are even and some of them are odd. So the transpositions are all odd, so they map to 1. And these transpositions are odd, so they map to 1. The identity and the 2 3 cycles, they're even, so they map to 0. Okay, and then the multiplication table maps down as well. And this group property is preserved. So notice that if I combine 2 even permutations, I get an even permutation. Okay? And if I combine 2, I guess what I'm trying to say is, yeah, if you combine 2 even permutations, you get an even. If you combine an even and an odd, you get an odd. And if you combine 2 odd permutations, you get an odd permutation. So if I share my tablet again, the fact that this is a homomorphism really encodes the fact that if you take permutations, and if you combine 2 even permutations, you get an even one. If you combine an even with an odd permutation, you get an odd permutation. And if you combine 2 odd permutations, you get an even one. Okay, so that looks a lot like the pattern of Z mod 2Z. Right? Just think of 0 as being even and 1 as being odd. So this homomorphism is really encoding a pattern. It's encoding a pattern that looks like Z mod 2Z, but exists inside this larger group. Inside this larger group, combining 2 even permutations gives you an even one, and combining an odd with an even gives you an odd, etc. I think I'll pause there. Any public questions? Thank you.